and morning to almost all of us. I don't expect people outside Europe. First of all, I would like to thank Eurobitume and Ian for inviting me to give this presentation in the Academia webinar. So Ian already introduced me. I'm an associate professor in chemomechanics of infrastructure materials. And today I'm going to talk to you about our work on how to use chemometrics or chemomechanics in order to engineer paving materials. So, of course, this work, I'm not alone, and it's not my, let's say, my own output only. So I have many collaborators. The content that I will show today, it is part of the work also of Dr. Ma. She's a postdoctoral researcher here with at TU Delft, Sadaf Kalihi and Mahmoud Kadije, and which are PhD candidates working with me the last 3 years. So I will start with the challenges that, and the focus today, you saw road infrastructure on the top. Of course, bitumen is not only a material that we apply for roads, but this is the main, let's say, application. So this would be my focus for today. However, similar challenges, let's say, exist also in other, let's say, construction, in general, the construction industry. But my focus today would be on the roads. So we do have quite a few challenges the last year. So we do see that the roads are used more heavily than we, let's say, designed for in some cases. There is climate change, which complicates things with respect to material performance and durability. Bitumen is a temperature-dependent material, as you all know. Therefore, any change, let's say, in temperature to start with will affect its performance. On the other hand, we do have extended service lifetime aspirations. We want our assets as roads to last for longer. And on the same time, we do also want them to be more sustainable and circular. I will go a bit on detail. What does it mean practically, at least for the Netherlands, Europe, but also for the Netherlands. I will focus a bit more on the country here. And at the same time, we don't have enough budget, and not a lot of new roads are built, at least in this part of the world, which means we are kind of more on a maintenance mode. We are looking how to maintain what we currently have. And of course, geopolitical, let's say, disruptions come. And events that cause volatility in the oil market prices. We are and have been experiencing this in different ways in the last years. So with all these challenges, actually, we formulate also in my group kind of the research focus. So where do we want to focus more? One part which is very important is actually degradation mechanism, so durability aspects. And for us, of course, we are a bit more on the research side, always with an eye to application. This is at the end our final goal. So it's more about understanding fundamentals, how, let's say, degradation happens in materials, and how these changes that we talked about, and we will talk about later, affect performance in the long term. Another very important aspect is prediction. So we would like to be able to have tools like models, but also more improved, I would say, or more reliable testing methods in the lab that could help us predict how a material will behave in the road. Another aspect that using also these first two, the insights of the first 2 points is the design of innovative paving binders. And In some cases, the technology itself might not be innovative on its own, but now we get more and more combinations of technologies together. For example, we have warm mix asphalt. This is not new. However, now we want to combine with, I don't know, very high percentages of recycling. Especially in the Netherlands. So then this creates new kind of materials that we will put in the road. And finally, technical, of course, aspects are important. At the end of the day, you want your material to perform for the application that you use it for. However, all the other, let's say, aspects around environmental circularity performance comes also into the pictures and become more and more important. So actually to have solutions, or the solutions that you have, the material solution that you have, they need, let's say, a more holistic approach, addressing both technical performance, durability, environmental aspects, and circularity aspects. I'm not forgetting, so I deliberately left out social aspects here. There is also the social performance with respect to social life cycle analysis, for example. However, this is not a topic that I will focus on in this for today in this presentation. So you are all aware of circular economy and sustainability targets set at European level. So we do want to let's say, reduce the pressure on materials and natural resource depletion. We do want more sustainable production, material production, construction, maintenance at the end processes. And now for the Netherlands, the goals are specific, as you see them in these 2 bullet points. So we aim to be climate neutral by 2050, but already with a 50% reduction in greenhouse gases by 2030, while the aim with respect to the use of raw materials is to reduce by 50% by 2030. So it's quite close, actually, in about kind of 5-6 years, and full circularity by 2050. And how does this translate, though, in practice? What does it mean? And in this case, for the Netherlands, already, I think 1.5 or 2 or almost years back, the asphalt sector actually announced that they will stop gradually. There will be, of course, a phasing out period, where the asphalt sector will stop with production of high temperature actually hot mix asphalt, as we know it. So we are going to go more on warm mix asphalt. At the same time, the ambition is actually to have mixtures that, as a typical standard mix to be used in the highways, would be warm mix asphalt with 30% recycled material. So this is actually the ambition, and there will be kind of a standard starting from 2025. There are, of course, specifications and other guidelines. They are already drafted. I think recently we had a final version for the warm mix asphalt guidelines for the Dutch from the Dutch organization, let's say. But this is something that we see it happening, and will be starting, or has already started, in the very recent time. And then we do have kind of more pressures. So changes in refinery processes. I'm sure many of you here, or all of you here, know firsthand about changes in processing crude oil. What does it mean? How do we get bitumen now for paving application? That the composition varies. We do have bitumen blends. We do have a lot of additives that are coming into the picture, from polymers, which is more typical, to plastics, rubber, also a technology very developed throughout the years, epoxy modified bitumen, bio-based additive, worm mix additives in case that you follow worm mix additives as your technology for lowering temperature, rejuvenators, another technology that it's very much used in the Netherlands, and especially not only to increase recycling rates, but also to rejuvenate or to extend actually lifetime. So we do have in situ rejuvenation. So there are all sorts of different, let's say, chemicals and additives and that are mixed together. And which brings us to how do we characterize these materials now? Because so far we mainly focus on empirical specifications. In the Europe, we use penetration grade as our main classification, let's say for bitumen. So no performance related. Of course, there are developments with respect to the use of DSR, for example, dynamic seriometer. However, there is still a need for more performance-based or performance-related testing specifications. And then there are other challenges if we go one level higher in terms of material scales. So now we are discussing mainly on the bitumen level or like a bitumen additive system. But of course, when we apply on the road, this is part of the story, even though very important, but there are also filler, there is a mineral phase there are filler, there are aggregates, there are different interactions with respect to adhesion properties, for example, between the aggregates and the bitumen. There is the structure material environment interactions. I mentioned climate change. There are many different things changing, conditions and changing on how our structure, let's say, experiences environmental stressors. And of course, we see slowly that there is a bit more variability on performance, and durability slowly degrades. So everyone is kind of alarmed, and we put a lot of emphasis on how to address these two aspects, actually, performance and durability, and long-term performance, but also variability. So am I sure that if I use a bitumen, what would be my performance at the end in the road? And here, if you see the second picture on the bottom right, it is actually a dike, because in the Netherlands, we do use also asphalt for the dikes. It's a covering for asphalt dikes, from dikes. So they are asphalt coverings, let's say, they call them. So it's very, very important part on how, and they face the same challenges as we do for the highway. So actually, I'm working on both topics also for the dikes, because they need to renovate also the dike, and we do have a lot in the Netherlands, but also on the highways. So challenges, if I'm going to summarize and also give a focus for today, would be how can we assess binders so as to make sure that they do perform well in the long term and they are durable enough, and how can we improve protocols, so tests, in order to simulate better field degradation, considering all this fundamental knowledge that we are developing as researchers, but also field data, so experiences as they come from practice. And my group is called Chemomechanics of Infrastructure Materials, and we are working actually to make these links, to link the material level, material scale, to actually performance at mixture and pavement scale under the influence of different environmental factors. So you can imagine that there is kind of a variety of techniques and methods that we use for this. Today, I'm going to focus more on the two middle, let's say, parts as you see them here. So chemical composition and rheology. So I'm not going to question how this chemical composition was achieved. What were the material processes or, for example, refinery processes that brought my my material to this composition, but also not to really link it to mixtures, but I will stay within the, let's say, chemistry rheology link. So we were talking about environmental material degradation. We do know that different environmental factors affect performance of bitumen. We call it aging, even though aging usually refers to oxidative aging. But when I use the term aging, it's more about environmental aging. So it's everything that can influence and can change the properties of my material, which of course in turn they will affect the properties of my pavements. And there are different ways for these, let's say, changes or this degradation to manifest at pavement level. The main, let's say, big aspects is fatigue cracking, low temperature cracking, and raveling. For the Netherlands, again, I underline this. We do use for our highways porous asphalt mixtures. So rutting, let's say, is not a very big problem. However, of course, in provincial roads where they use denser mixtures, this also come into the picture. So what have we been seeing also from literature, but our own experience? We have been doing many tests. I will show an example later, and we have seen that there is a big discrepancy between laboratory and field age samples, and which actually makes sense. As, for example, you can imagine that you see the pressure aging vessel on your right in the picture. It is a technique that uses pressure, time, and temperature, while of course in the field there are many more factors that come into the picture. So this could be already one reason why there are differences between the different results that we see between lab and field. Not the only one, but with respect to durability and aging, how to simulate environmental aging, we feel this is an important aspect. So what we aim to do, and what you will see a bit later, is about that we try to understand how the individual and combined effects of aging affect actually performance, bitumen performance, and which are the essential or the critical factors to integrate into degradation protocols of the future. And we do use advanced analysis methods. I will show some examples in order to make the most out of the data, actually, in order to be able to maximize the amount of information that we are able to get from standard or semi-standard, I will explain what I mean, or from tests that are used typically of course, in research, but also in practice to characterize bitumen properties. So to focus a bit more, we were thinking, okay, how can we improve laboratory aging procedures? What would be the main factors to include, as I said? And this project specifically comes as a request from our Ministry of Roads, let's say, for infrastructure, and Rijkswaterstaat in the Netherlands, where they do want to include new testing methods or improve current testing methods that they have in their so-called blueprints for material characterization. So how we started, of course, with laboratory experiments. We tested many bitumens in different conditions. We used two main characterization methods, or I might say, I will present to you the two main characterization methods, but we used much more methods. So there there is Fourier transform infrared spectroscopy and DSR. So these are the two that we used. And then we use different analysis methods, as I said, to maximize the information that we get out of these tests. And finally, we wanted to validate, compare, and check how all of these, let's say, laboratory experiments and methods, they do really relate or not compare with respect to field age samples. So also we have been monitoring specific tests. Yeah, it's not a test section per se, but it is slab. So we made some test sections that we have been following in the last 10 years in order to be able to understand and make these connections. So this is a big matrix for the specific thing, like a flow chart of the methodology. So as you will see, we applied many different conditions. We have different, two different binders. We do have different mixtures, and we do have the same mixtures in the lab, but also in the field. And then we did all sorts of aging aspects. Then in some cases, we needed to recover some binders when we had a mix. In others, we just, let's say, homogenized and blended better the binder as we, after aging. I will show FTIR and DSR, and we use different techniques in order to analyze the data with specific aims. Here you can see the aim. So in other techniques help us understand what is the effect of aging factors and back calculate field aging conditions. Other techniques, they help us classify and different types of bitumen based on their aging and composition type, and others actually help us make the equivalency between field aging and lab aging. So I will show some examples as we go. So this is a big testing plan or material testing matrix where it shows the different conditions. We tried to develop a protocol, as we said, that could incorporate different factors, but also, of course, in the lab, we want to have accelerated phenomena. Therefore, we also varied thicknesses. What is the thickness of the bitumen? Standard thickness, for example, for PAV is 3.2 millimeters. So we try to reduce the thickness in order to accelerate phenomena, but also play a bit with the temperature, pressure, etc. This is the field age samples that we have we used as references for this part of the analysis, because for the bigger, let's say, project, we did also use field age samples really from test sections from different areas, from different parts in the Netherlands. But for this one, we had made already back in 2014. So 10 years back, we built two sections, one porous asphalt and one stone mastic asphalt. And from then onward, we sample once per year. Now it is one per year. Earlier we did even 2 times per year, but now we are starting running out of material actually. So we have to be a bit more selective for our coring and sampling. Therefore, and then we take the cores. We also are interested in seeing, especially for porous asphalt, the effect in depth of aging in the depth of the layer, of the surface layer. Therefore, we cut the sample into 3 slices, and we every time first we test the core as for stiffness and strength, and then we further slice, and later we extract bitumen where we test it. So this has been, we have been doing this exercise already for 10 years, and looking at the material that we have, I think we can go another 3 to 5 years more, depending on the type of tests that we would like to do. You understand that this is a very big advantage because we do know exactly how we made this. The materials used are exactly the same. So we do have really the starting material, but also the same material after so many different lab procedures, but also filled. And this is some preliminary results, like until 2018, you see here, where you can see, for example, these two circles here show the long-term and short-term aging phenomena, while the other ones, as you will see them, it is the different years, starting from 14 and going up here to 18. And in each circle, bigger circle, you see 3 points, which actually are the top, middle, and bottom slice from each top surface layer, top layer. So you can see, as we started here in 2014, the properties, let's say, among these slices were very close to each other, but as the years go by, you can see that there is really a gradient happening in your pavement with time, of course, with the top of the top slice of your surface layer being more aged than the bottom part of your surface layer. So we have all these materials, as we said, we collect all this data, and what we do is FTIR. So this is the main method that we use. And for this study, we use specific functional groups. This is the carbonyl, sulfoxide, sulfones, aliphatic, long-chain aromatic, and hydroxyl groups. This is the groups considered, the indices considered in the study that you are going to see later, in the results you are going to see later. And of course, DSR, this is different conditions here. Yeah, they have a kind of their own, of course, coding, and you can see the evolution, let's say, or the changes in stiffness, complex shear modulus, and phase angle with different aging conditions. And what do we take from this? We take, as we said, these functional groups. This is how we define them. The indices, and then we use, let's say, the sigmoidal model, where we have different parameters in order to actually model the behavior and the master curve, as you saw it in the previous slide. So the data sets that we use, they consider of all these parameters that gives us the main chemical information as they come from FTIR spectroscopy, and we use the sigmoidal model parameters with the shift factors for different temperatures and the crossover values of the rheological data. So all of these are collected for each bitumen that we use and for each condition that we have. So you can imagine that there are quite some data there, and we combine together. So we have a combined aging index, which actually it's a way to express all these indices in one single value. I will not go into the details how it is done, but we do have publications about it, so I can share with you later if you would like. And of course, the rheological data set, which is, as we said, the sigmoidal parameters, crossover values, and the shift factors as we from this data. So usually, previously, actually, what we will do, we would look at the different parameters, like, I don't know, with aging carbonyls increase or sulfoxides increase. At some point, we see a plateau with time, etc. Or the master curve, G goes up, phase angle goes down. And this is the usual evaluations that we did with respect to understanding how bitumen is affected by aging. However, we feel that this is not enough at the moment. The complexity, let's say, of the materials that we have, and they do create the need to go further. So we use different statistical tools. I'm not going to go into big detail, but we use principal component analysis and linear discriminant analysis. All these methods are under the multivariate statistics that they are used to analyze and to find let's say, patterns in relationship between multiple variables. And in this case, we do have multiple variables, as we already saw. So how do we use it? So if you run such analysis, let's say, with the data that we have there, then you can get this type of information. So for example, here you see different bitumen types. 446, it's for 4060, of course, 710 is 700. PMB is the one with SBS modified bitumen in this case. And there are three different bitumen types, Q, V, and T. And this is the names that we give them. And you can see already that we can have a very good classification based on the type of bitumen that it is there. So, for example, you can see here that you have the two bitumens, three actually, bitumens here together. This is the T bitumens. And there is kind of a slight shift based on the grade of bitumen. Here you see the blob of the Q bitumen on that side with V. And we do have, of course, some differences. For example, we would expect that Q bitumen will cluster more with his own family, but this was not the case. And of course, we are not. We don't know the exact composition with respect what were the processes that this material went through. But apparently, there is something that creates this classification. What we can learn from this, though, it's these algorithms can tell us actually what were the discriminating factors used and what were the discriminating information used to make this classification. So from this, we can understand also what are the more influential indices or factors that we can check in order to evaluate differences between different binders. And this is actually one of the strengths of these tools as well. This is another example, again, a binder classification, but now it is the same bitumen, but with different aging status. So So we start here from the fresh and oven, and as we go from left to right, we see an increase with aging and changing happening. So you can imagine that this could be quite interesting if you have a bitumen with unknown, let's say, origins or something, or state of aging, or you get a filled bitumen, and then you have such a map where you can place your bitumen, position it to the right place. Then it gives you already quite some information where you are with respect to this service lifetime and durability, as we were talking about earlier. Another thing, now we have one bitumen, but also we brought the lab-aged mixtures there where we extracted bitumens, and we do have all sorts of field data put there, and you see already the clusters that they form. So porous asphalt is somewhere here. Here we have, this is the field, actually the 3 is the field, the 2 is more the lab mixtures, and this here is actually the binder test. So you can see how they classify and how close or far they are. Why is this important? Because we can use this information also to tailor our laboratory protocols in order to meet better, to come closer to actual field conditions. So this information is already for us important. Other analysis, you can use support vector regressions. This is a machine learning tool and can give us actually relations between rheological parameters like alpha value. It is one of the parameters of the sigmoidal model that relates to the stiffness of the material, and specific ranges of FTIR. This actually is the region between the 734 and 783 inverse centimeter, where actually shows that there is a bit of good relationships with respect to stiffness, which actually makes sense because this region corresponds to the aromatic groups, which actually are quite, let's say, impactful with when we come to the stiffness of the material. Or there is, let's say, another region here that also correlated very well with stiffness aspects. and also it makes sense because here also you have some sulfur also, functional groups, related functional groups that are quite influential in terms of cross-linking, for example, and in this case we did have a good correlation between stiffness. So based on these relationships, we can actually try to see what are the chemical information that affect our performance or rheological performance for our material. And how do we use it? So we use different techniques in this case, but the final outcome is actually that we go towards predictive models. So in this case, we were able to say that if you take your material and you age it in these conditions, then you simulate so many years of field aging of a porous asphalt mixtures. You can imagine that this is, of course, based on a specific data set. So now we are trying to extend, but these tools, they can help us in making these relations between field and lab aging. And this, you see, there are different conditions in this table, the sample names as we call as they are here, and of course the predicted years in the field. Of course, 0.57, it's too accurate in this case, and this is not, but you can imagine the idea that this would only simulate half a year in the field, and as we go to more severe or more kind of strong conditions, then we can simulate more and more. And the idea is that these two should match chemically and rheologically. Yeah? This is the critical point here. Of course, you can also take a big hammer and start hitting your material. You will also create some damage, but then here the objective is that chemical and rheological profile of field and lab match with each other. So how to apply in practice? So we use FTIR DSR for binder characterization. So we can get more information out of it and understand what is the actual relation between property and chemical properties and performance properties like rheology. And we can use such models to classify binders. So actually, it is important because we can identify where in this map of bitumen, different bitumen types, an unknown bitumen can fall. And also we have machine learning aspects where they can help us with prediction of properties and of conditions, and really how to bring closer field and lab aging protocols. Lab aging protocols with field aging. Of course, all of these are good. They do require data. So we are lucky that we have quite a lot of data already. I mean, our PhDs or the researchers here work with different data sets. So we try to update the databases and rerun the models, train the models, especially the machine learning models. They need a lot of information to become more and more accurate and reliable. But of course, there is always a challenge, a big challenge, and I will just, I'm a bit slightly over time, I think. I will just close with uncertainties. Uncertainty is a big issue. All these techniques, as I said, they need data. You can, and of course, they have some margin of error. As any prediction or any model, actually. So what we want to also do is actually to really quantify uncertainty and put it into the output, into the answer, into the prediction. And how can we do this? This is an example that we use another machine learning tool. And in this case, we don't use FTIR, but SARA fractions in order to, and some physical properties, in order to predict from this input data, actually predict the master curve for our bitumen. So the input data, imagine it can be experimental databases, with all these conditions that we have. We can test for this, we can specify the conditions, but also some of these, they come from other models, which is finite element models, which are validated, of course, with tests, and then we run them many times in order to increase the amount of input that are needed for such machine learning method. But of course, this you can see, you train your model, and there is an ideal fit, and here you have a very good prediction with a 0.092 and 97, but here you are in the training phase, so you actually feed data to your model in order to learn how to do it. You train it, and then of course you need also to test it, and naturally your accuracy, of course, goes a bit down. Before it was 92 and 97 for the complex shear modulus and phase angle, as you can see it. But of course, when you use now your testing data, so you actually test what it learned, of course, the prediction that it gives you is a bit lower. And another issue is that if you run now the same machine learning model many times, and this is different runs, as you see, so first run, second, third, and you predict the complex shear modulus and delta and phase angle, then every time you will get a slightly different answer. So every run that you do, and this is what I show here, it will have a slightly different accuracy, let's say, and will give you a slightly different answer. This is because these models actually are not deterministic. So they can have variability and uncertainty, which is related to the data on its own. There are data sets that are noisy, there are errors there, measurement errors. There is also randomness, as I said, there is no deterministics. Let's say these are not deterministic models. There are also model uncertainty on its own, because sometimes the architecture, as they call it, so how many of these nodes here and layers you will take, it makes a difference in the prediction and the outcome of your prediction. And all of this, of course, they do create some uncertainty. And for me, uncertainty, what does it mean? Is if I run it one time, it can give me a G star of 2.99 to the power of 10 to the 8. But 10 to the power 8, and the other time can give me a 2.3. You cannot say it is wrong, but it is different. And usually we aim to get one answer, but this is not the idea, because we need just to consider this uncertainty, to my opinion, and have a kind of a range of values, or a range, a typical range of value, and quantify this uncertainty and use this information in order to take risk into account and to make informed decisions. So in this approach, we reject the idea that only one function can describe, for example, a master curve in this case, the points that are given, and these big data sets that we have, but there are all sorts of possibilities with a specific probability to each of it on how to go and simulate and model and fit these data points, and which creates a prediction with uncertainty of quantification. And this is actually what we are working on. So my PhD Mahmoud is working on a combination using machine learning with a quantification of uncertainty, in this case with using Gaussian regression, but this is too detailed, in order to get outputs that gives you also the uncertainty of the data, the uncertainty of the answer that you get. In these cases, we again predicted G star, so complex shear modulus, and you can see this is the gray area around it is a plus a minus 2 standard deviation range. So we give you an answer. So if someone asks me, can you predict based on these Sarah fractions and conditions the G star, for example, I could say yes, it would be, for example, 2 plus minus 1. So you have already a range, so you know that you could have a value within this gray box here. Similarly, the same for delta. you can see the challenge of modeling delta, actually, phase angle. So the gray area, let's say, becomes bigger. And because we didn't have a lot of data at very low temperatures, you can see that the uncertainty here goes very high. But now we do have the power to understand, actually, how certain or not is the number that we are going to get. And I feel that it's a very strong, it's a strength if you have to make decisions, if you have to make some, let's say, selections or compare or evaluate specific materials. So ambitions and steps forward. So we are using all these tools that have like scientific, they're heavy on the science of it in terms of methods and analysis. However, our aims are quite practical. So it is to develop protocols. Part of the project that we are working with the ministry, actually, we are going to now propose a protocol to be used that we are validating with more and more materials as we go. Another is that we can use such tools for fingerprinting binders, so for identifying actually what are the state in terms of composition and aging. There is already a RILEM committee, technical committee on fingerprinting of bituminous binders, where Professor Hofko from TU Vienna is the chair and I am the co-chair, where we aim to have a pre-standardization of FTIR as a recommendation, as an output of this committee, on both aspects, so how to perform the test, but actually how to analyze the data. My group is specifically focusing on the tools for the analysis of spectroscopic data. We do test and we do get information of other technologies. In this case, in the Netherlands, in situ rejuvenation is very relevant. So this is what we are trying to work on. We are working on. We want to predict performance level, and we want to validate our tools for more and more materials and technologies. There is a variety in materials and technologies, as we said. So our aims now to see if these insights, if these relations work also for these mixtures, like doubly low temperature mixtures, for example, with high percentages of recycling. And can we find additives, or can we identify groups of additives that has a kind of an anti-aging potential? And finally, going towards testing specification. So we do understand and we do see that we need better test and analysis methods that are more create this link between material composition and performance. And these tools helps us understand these relationships and focus more on what is the more critical parameters to test. And this is what we aim to do here. And finally, the acknowledgements, of course, all of this work and I mean, we need people and we need resources, so we need budget and money. So this work is mainly part of MAFRIN, which is a multi-scale approach towards future road infrastructure. It is funded by our national Dutch here Research Council. Then we have Rijkswaterstaat, which funded 4 years, and now we are happy to start with another 4-year program as a follow-up of this on knowledge pavement engineering. My work will focus on durability of new materials, or new with respect on the use and more intensive use in the Netherlands. And of course, we have CERCOM, which was financed by CEDR, and CERCOM touched upon and is touching upon the environmental circularity aspects. I didn't go into this because of time. I'm already a bit over time, but this is the holistic framework that we're talking earlier about. And with this, I would like to thank you for listening, and I'm happy to discuss and answer any questions that you might have. Thank you very much.